For a 1D system, this is how we define the potential energy. And if you take the change in potential energy for a small change or small movement of the particle, so from x plus delta x, from x to x plus delta x, this is what we get. And since it's a small movement, so we can assume that the force does not change in that interval. So we can take the fx out of the integral, okay, because we have moved a slight distance. So I can say that in that small delta x distance, the change in potential energy, the force is can be assumed to be constant. These are the ideas of calculus. So we take it out, and then what we get is delta x. So what if f is a function of x for a 1D system, this becomes delta u by delta x, and if you take the limit delta x tending to 0, you get du by dx with a negative sign, of course, in the limit that delta x tends to 0. Now this is for a 1D system, and we generalized for a 3-dimensional system the vector f as a function of vector x in this case is minus grad of u. This is how things get generalized. That du by dx for a 1D system becomes a grad u for a 3-dimensional system. Right. So this is what we discussed in the previous lecture. Now this lecture we talk about stability. So let's say you have a simple spring mass system. The spring has a spring constant k, and we have an equilibrium length. Let's say we call it x equal to 0. So x equal to 0 is the unstretched equilibrium length of the spring. So for this, if I was to draw the potential energy function, what will I get? I get a parabola, right? So x equal to 0 has the minimum energy, and as you go away from x in the positive or the negative direction, the potential energy increases. Let's look at 3 points, A, B and C. So at A, what we see is that du by dx is greater than 0. F was minus du by dx, so f becomes negative. So that is towards the origin. At B, what we see is f is positive. So B is at x negative value, at a negative value of x, again towards the origin. And what happens at C? There is a minima for this curve, for this parabola. So du by dx is exactly equal to 0. F is also equal to 0 because f is minus du by dx. So I'll write some conclusions here. One is, for this particular case, force always towards equilibrium. I'll write it as EQ in this lecture. And F is equal to 0 only at x equal to 0, which actually is the minimum for the U curve. You'll read my writing, right? F is equal to 0 only at x equal to 0, where there is a minimum for the potential energy curve. X equal to 0 is the equilibrium position. If you do not touch it, and if the system has some non-conservative force such as friction, after some time it will sit at x equal to 0. That's an equilibrium position. And if you are at an x value greater than or less than 0, then it tends to go towards x equal to 0 for this particular system. We know that, it's intuitive. Is this equilibrium stable? What is the meaning of stability first? Answer that question. Equilibrium is where it can actually sit. If you leave it there, it will sit there. But a stable equilibrium means if you displace it away from the equilibrium, it will come back. So I said equilibrium point is the point where the potential energy has a minimum. I'll generalize that statement. I'll say if it's an extremum point. A maximum will also be an equilibrium. But for this particular case, this equilibrium is stable. Now look at this this curve. Now take an analogy with actually a bowl. It's a bowl. There's a ball sitting at the bottom. You take it, leave it, it will come back. Just an analogy, nothing else. Okay. So this is a stable equilibrium because any displacement, any means in any direction, brings it back to equilibrium point. Now I'll say wherever you have du by dx equal to 0, that's an equilibrium point. So for a potential energy that looks like this point C prime is also an equilibrium point, but this is an unstable equilibrium point. Why? Because even a slightest of the displacements will take it away from the equilibrium point. It will never bring it back. But nevertheless, it is in equilibrium because du by dx is equal to 0 at that equilibrium, at that point. Is that clear? Let's take an example of a pendulum. So you have very light rod of length L, and there is a mass m that hangs from it. It is displaced at an angle of theta from the vertical. So let's say this line where the height of the mass at theta equal to 0 was the reference position. So the height of the mass is L minus L cos theta. So if I write the potential energy as a function of theta here, that makes more sense. Rather than taking it as a function of z, we take it as a function of theta. That's mg times L into 1 minus cos theta. Let's find out the extremum points for this. So du by d theta becomes mg L sin theta. And when is it 0? When theta is equal to 0 or pi. Well, in this case 2 pi again means it's the same thing. So there's no point saying n pi. So theta equals 0 or pi. So we have two equilibrium positions. Theta equal to 0 is stable. Check it. Okay, it's a minimum. So d2 the second derivative with respect to theta is greater than 0, and theta equal to pi is unstable, as you will see that the second derivative less than 0, it's a maximum, but both are equilibrium positions. So we'll conclude that this system has two equilibrium positions. One is at the bottom, that's a stable one. You displace it, it tends to come back. One is at the top. We have all played around with a pen or a spoon or some people who really are into equilibrium, they'll take glasses, put a spoon, another spoon, and when you're getting bored, you do that in the restaurants. That's the sad thing about engineers to be. All you can do is you can even do stability even when you're getting bored. Okay? It's physics all the time. But that's okay, that's how we are. There's nothing we can fight about it. So that's equilibrium, but that is unstable, and that's very interesting. It's very exciting to play around with unstable equilibrium. Okay? Slightest of the nick and it goes away from the equilibrium point. And in reality, that slightest of the nicks can be anything. It can be the wind blowing, it can be vibrations in the floor, anything. So these systems are called unstable systems. In fact, unstable systems, you can't even hold them unless you keep moving the pivot. Then it becomes a very interesting, very interesting dynamics problem. Unfortunately, that is beyond the scope of this course. But people who take up advanced courses, you can actually solve this problem of a pen, like what should be the vibration, what should be the movement in a one dimension, let's say, of your pivot, so that a system which has a certain kind of stability graph will remain stable. These are interesting problems, and these are actually used in control systems where you want to actually ensure stability of systems. So you have these companies which are making robots, bipedals, Boston Dynamics, for example. So it's very difficult to keep them stable. So you have to actually solve these problems, and again then put some active controls as well. There are also systems which look something like this. Anybody knows what these are called? So this point is called metastable equilibrium. It seems to be stable, right? You move it slightly, it stays there. But a large enough push and it goes away. The metastable point. Again, you will find these kind of, and then they are very deceptive, in the sense that it may seem that you have a stable equilibrium, but you go a little bit away and then it becomes a problem. So when you're designing a ship, for example, it may seem that I've done an experiment, I give it a slight push, it stays stable. But if you go into a storm where the push is not that slight, and you will see the system was actually metastable, then it will topple for a large push. Okay? So these are called metastable systems. And you also have a neutral equilibrium. Flat floor. Put a ball, give it a push, it happily goes away, never comes back, never goes away further as well. There's no desire, there's no potential energy change. So this is where all the derivatives with respect to theta are 0. So this is called neutral equilibrium. Now there's a very interesting toy. It's called a teeter toy. Anybody seen that? You've seen that toy where you have a bird with large wingspan and you balance it on its beak. You'll see it as a showpiece in many offices or houses. There's a bird balanced only on its beak. Very large wingspan. Okay? Something like that. And there are many toys which look very similar. But the idea is, it's very weird to see. There's a bird and the beak is in the front, but still it is balanced on that. And you give a bird a shove, it just stays balanced. It's a very stable equilibrium. you have a pivot. Everything is almost massless except the two masses m, each symmetrically placed, attached with a rod to the pivot, and the angle is alpha on both sides. Symmetrical system. And this is balanced on a surface. Now what happens is, I ask you this question, well, this is supposed to be symmetric, it looks slightly unsymmetric, asymmetric, better. So I ask you, check if the system is in a stable equilibrium. What will you do? You will calculate the potential energy function, let's say as a function of theta. So you take this and you give it a displacement. Now this is exaggerated, but let's say you give it an angular displacement theta. So this angle is theta, and we calculate the potential energy now of the two masses. So what we do is, as a reference, we take the potential energy at the pivot equal to 0. I will not do that, it takes some time to draw the diagram and show you, but what has happened is, one mass has gone down, the other mass has come up. So the potential energy of one mass has increased, one mass has decreased, not in an equal sense, but it has the overall system of two masses has a new potential energy now. So let's write that. So I'm writing it from this reference of the pivot. This is one mass. Capital L, I didn't tell you, so this is the length. Small l is this rod. Writing alpha plus theta and alpha minus theta for convenience. And then you apply the property of cos alpha plus theta in terms of sin alpha sin theta, cos alpha cos theta, and cos alpha minus theta, and expand it. So I'll write the final expression. Okay. That's more important. So u as a function of theta is twice mg cos theta times capital L, that's the length of that pivot rod, minus small l cos alpha. Small l is the length of the long rod that connects the masses with the pivot rod. So to check for equilibrium, we check when du by d theta is 0. So for this we see this becomes twice mg sin theta times capital L minus small l cos alpha, that's equal to 0. So now tell me, when does this become 0? Don't worry about how we got this. This is simple geometry, nothing else. I need help now. Alpha is constant, okay, don't get confused. It's only theta that is variable here. So what is the meaning of theta equal to 0? That's where we started with, right? What is theta equal to pi? That has no meaning for us. Okay. If the ground is flat, it cannot go inside the ground. So theta equal to pi has no geometrical significance or physical significance in the particular situation. So it's only theta equal to 0. Is that it? No? So what about it? It's good. So what about this thing? So that becomes important when you want to check whether the equilibrium is stable or unstable, and that is what we have to check, whether that toy is in a stable or unstable equilibrium. Okay. So when is it a stable equilibrium? When it's a minima. That means this d2u by d theta 2 has to be greater than 0. So when you do that, when you take another derivative, so basically what that boils down to is that your L minus small l cos alpha has to be greater than 0 for stable equilibrium. So capital L minus small l cos alpha is greater than 0 if your mass is attached such that it is below the pivot. So the masses should be below the level of the pivot for this system to be in a stable equilibrium. You can make it if somebody is motivated enough, you can actually make it with sticks and all, or you can have a more interesting system, 3D printed, or some rods and all with some screws, so that you can change the angle. You can see as soon as you take this below the pivot, it becomes stable. You change the angle alpha such that the masses go above the pivot, it becomes unstable. You can't even balance it because it's unstable. But if theoretically you could balance it, you could give a slight push, it does not come back to the equilibrium position. Is that clear? So typically for equilibrium, we are interested in finding out whether, so the first question we have to answer is, what are the equilibrium positions? Second is, are these stable, unstable? What kind of equilibrium? Metastable is a little difficult because then you have to, locally it will be stable, so you can, with derivatives you can only figure out whether it's stable or unstable. And there is another thing that we have to work on, that is how stable. So that how much of a stability is there, that is answered through the oscillation frequency. You all solved those problems where you take a mass of a block of wood, put it on a water, put it in a water bath, give it a slight push, it starts oscillating. Find the oscillation frequency. We have all solved those problems, right? And we loved them. The problems where you have to find the oscillation frequency of systems. This is where we also discuss it in a bit of a further detail. But before that, I would want to talk in a general sense about energy diagrams. Let's visually look at stability. So this kind of a diagram we have seen for a spring mass system. This is called a harmonic oscillator. So let's say your mass is at the equilibrium position. I give it a pull and leave it. So when I give it a pull, I give it some energy. The energy I give it is, so this is an energy diagram. So basically on the y-axis, you have your energy, and on the x-axis you have your x. So this, this let's say is x equal to 0. So when I give it a pull and leave it, I basically give it some energy, right? And let's say this is there is no friction here, so it's a conservative system. So E is constant. At any time, you will see that the energy is constant. Now energy is equal to potential plus kinetic. So I can say kinetic is equal to E minus U. So through this diagram, I can tell you that the particle can only stay between these two crosses. It cannot go beyond x maximum, which is this one. It cannot go beyond behind x minimum. It will only stay between them, because that's how much energy it has. I gave it a pull and leave it. I gave it a pull which was equal to x max, and x max actually the modulus is equal on both sides in this case. So it's a bounded system. So what I have done is I have shown you the potential energy graph, and I have drawn a straight line which is the energy for this conservative system. It's a bounded system. It cannot cross the two bounds, the lower and the upper bounds. So k is max at x equal to 0, and k is 0 at x min and x max, because k is equal to E minus U. So you can see from the graph that your U becomes, your potential energy graph intersects the equal to constant graph. That means at the extreme points x max and x min, your potential energy is equal to E. So k is equal to E minus E, that is 0. But that E can vary. E is dependent on how much energy I gave the system to start with, right? So what happens is, if I increase the E, that means I am increasing the amplitude, and if the E is low, that means the amplitude is low. No confusions here? Any questions? Are you all clear with what's discussed? Now let's have a more interesting. So this is another potential energy graph. So this in fact is a constant upon R, or constant upon, yeah, R is fine. So this is your R axis. So it's basically a normal reaction, electromagnetic forces. So if I take the molecules on my foot, if I put them on as I get them closer and closer to the surface of the ground, there is repulsion. And as they get closer and closer, the two particles or the two molecules, whatever you want to call them, the repulsion increases. And what is repulsion? Increase or decrease in potential energy? Increase, and that is what we are seeing. As R is decreasing, it's asymptoting. Okay, so this is for a force, which is A upon R square R hat. Inverse squared force, as they get closer, the force is increasing as 1 by R squared, and it's in the direction of R hat. So it's outwards. All right, so what we do is, we have given the system some energy. So let's say this is the equal to constant line. And let's say you start with this value of R, and the system is moving towards R equal to 0. Agreed? Now what happens? The two particles, let's say one particle is fixed, the other is moving. This particle is moving towards the other particle with an energy E when it is at a value of let's say Rp. It gets closer and closer, and it cannot go closer than this point. So this I call R min. Then what happens? It changes direction. It's a conservative system, right? So it reaches there, sort of rebounds or collides, and then comes on this direction. Now in this direction, what happens? Does it stop? Kinetic energy is E minus U. When it was getting closer to R min, its U was increasing, K was decreasing, because E is constant. And then K became 0, but now it starts moving away. So now U is decreasing, K is increasing, but U keeps on decreasing. That means K keeps on increasing. The particle just accelerates away and away from the origin or from Armin, whatever you want to call it. So this particular diagram is showing an unbounded system. It's bounded from one side, but overall it's unbounded. Is that clear? If I just show you this potential energy diagram, there's a lot you can understand from this. And these diagrams actually are called energy diagrams. They are used for a lot in physics, particularly where you talk about molecules. So when you get molecules formed, then you see energy diagrams that correspond to the potential energy of the 2-atom system or 3-atom triatomic system and so on. But we also use this for other kinds of ideas as well. Now I told you the particles collide at Armin, right? It's as if they are colliding. I mean, this particle was coming closer and closer. It hit at Armin because it cannot go any closer, and then it rebound. But what if I shot this particle with a larger energy? Will it collide at Armin or a different distance? It will come closer, right? If you had this much energy, it would have reached this point, a different Armin. So I can say that there is collision between the particles, but the distance of collision depends on the initial energy of my system. Good. So let's take another system. Or R. And this is an attractive system. At R equal to infinity, when the particles are not interacting at all, your energy is, potential energy is 0. But as you get closer, since it's an attractive system, then the potential energy reduces. Again, you can interpret ideas similar to that, but now we'll talk about a system that is more realistic, that is seen in diatomic molecules. And you will see this diagram at a lot of places at different times. Have you ever seen some kind of a diagram like this? Where have you seen this? Where? Where have you seen this? Chemistry? Do you still study chemistry here? No. Material science, yes, you have studied that. But that's not a compulsory course for everyone, but the lucky ones have studied it. So what's happening in this region is repulsion dominates, and in this region attraction dominates, right? At infinity the potential energy is 0. There is no interaction between the particles. U equal to 0 is what we take a reference. As we get closer, they start attracting, so the potential energy reduces. But then as you get closer and closer, the repulsion starts dominating. So this is what we get. At this point, the force is 0 because du by dr is 0. This is an equilibrium point. Stable or unstable, you can figure it out yourself. Now let's see if we give the system some energy, let's say E. It's a bounded system, right? Can we see that? What about if I give it large enough energy, such as this one? This becomes unbounded. The same system. So what do we learn from here? If you want to break a diatomic molecule, you have to give it enough energy so that it jumps from this boundedness to unboundedness. You give it a positive energy, so that's the reference we have defined, it becomes unbounded. The molecules, the atoms go away from each other. Okay? So the same system can be bounded or unbounded depending on the energy it has. Good. So let's come to oscillations. I've drawn many systems in front of you. So this is some arbitrary shape. It's not x equal to, it's not a parabola. Some arbitrary shape, but we know that it has an equilibrium at x naught. I want to figure out what is the oscillation of the system about x naught. What is the frequency of the oscillation about x naught? Taylor series, do we remember that? Good. So this is x naught. So the potential energy at a slight displacement away from x naught is what we want to calculate in terms of the value of the energy at x naught and its derivatives at that's what Taylor series tells us. It gives us the function in the domain it is analytic. So near at a very small distance away in the neighborhood it is analytic. So we can write u at x naught plus delta x in terms of the information about the point x naught. Okay. Now this delta x is very small. So I will say that delta x squared is much smaller than delta x and so on. So I will only retain the first derivative. So what that, and by the way, sorry, I don't want to do this. Actually this is 0. That's an equilibrium point, right? So du by dx at x naught is 0. So when you are adding things, this becomes, so I want to calculate the change in potential energy, and that is I only retain the first term because delta x cube will be much smaller than this one. By the way, what does this look like, this delta u? Like half kx square. Harmonic oscillator. So I will conclude that any system close enough to the equilibrium point behaves like a harmonic oscillator. If I want to find, I can model this system as a spring mass system where the spring constant is given as the second derivative of my potential energy function at that point. Okay. You can also think of it as because if you think of it in terms of force, you can also conclude this. So basically this means the force is restoring force is like minus kx. So any non-linear curve very close to a point looks linear, right? You take x cube, you zoom into it, get closer and closer. Very close to that point, it will seem any curve will appear linear close to, very close to a point. The same idea of Taylor series. You can write f of x plus delta x, then you will see it's only the first derivative that matters, so it shows like a linear. Good, so now we have something to work with. Now I can calculate the oscillation frequency. We are out of time, I can't do that. In the next lecture, we will do that. We'll calculate oscillation frequencies for the theta toy. Now, if you are motivated enough, try it yourself. Thank you.